This introductory lecture opens the set of lectures on the principles and applications of piezoresponse force microscopy and spectroscopy. In brief, piezoresponse force microscopy is the technique for probing electromechanical coupling on the nanometer scale. And it is incredibly useful for studying materials such as ferroelectrics, batteries, fuel cells, memristors, polymers, biological systems, and maybe coming applications such as molecular machines and many others. It is interesting to see what was the origin of the PFM. And it turns out that we can trace it back to the experiments by Luigi Galvani in the 18th century, who applied the electrical bias to the frog leg and observed how the frog leg started to twitch. And these experiments are most famous for the discovery of electricity and giving the English language the words such as galvanic or galvanize, but it was also the study of the electromechanical coupling. And given that now we are in the 21st century, the question is, can we extend Galvani's experiments to the level of the individual molecules or unit cells? And to do that, we need to see what are the length scales at which the electromechanical coupling originates. And what does it tell us about the materials? Imagine that we have a single crystal of quartz, which is one of the most famous electromechanically active material. If we take this crystal and put two electrodes on it and apply bias, we can directly study the electromechanical coupling. We can also take this crystal or a part of it, go to the synchrotron and study the properties of the materials on the level of the unit cell. So we can study structure, phonon modes, and other materials properties. And then we can directly compare the macroscopic electromechanical properties with the atomic structure and phonons. This approach, however, no longer works for biological systems. For example, if we take a mouse and apply electrical bias, the mouse is very likely to respond very strongly. However, we no longer can go to the synchrotron and understand what the mouse does based on the scattering results. In fact, we need to study this electromechanical coupling on the level of tissues, on the level of cells, and ultimately on the level of the single molecules. However, even for an organic system, we also need to study local phenomena. For example, if we have a ferroelectric material, very often it will exist in the form of multiple domains. There are other materials such as relaxed perovskites which phase separate and form these rather mysterious 10 nanometer size regions. And generally, we need local techniques, or in this case, scanning probe microscopy, to image and quantitatively study the elastic electromechanical and electrical behavior if we want to understand these materials. So, how are we going to do that? First of all, let's define what is the electromechanical coupling. So the simplest example of electromechanical coupling is so-called direct piezoelectric effect. Imagine that we have a crystal, we mechanically compress it, and this creates charge on the opposite side of the crystals, and this is what is used in the zepolators. There is also the inverse piezoelectric effect. When we take a crystal, we apply bias to it, and then the crystal starts to change its shape. It either expands or contracts under the action of the electrical bias. So in the coming lectures, when I talk about the electromechanical coupling, I will typically refer to the inverse piezoelectric effect. So, does it appear only in crystals, or does it also appear on the smaller length scale? So let's go all the way to the very small length scale in the case of a single chemical bond and see what is the magnitude of the piezoelectric effect for the single bond level. So in this case, it is really easy to analyze. If we take the single molecule, put it in the electric field, it is very easy to calculate the effective piezoelectric effect from the charges and the force constant of the bond. And it turns out that for proverbial molecule, the piezo effect can be of the order of 10 picometers per volt. So it is pretty comparable to materials such as quartz or materials with a strong piezoelectric effect such as PZT. So generally, electromechanical coupling is ubiquitous in the system with the polar bonds. So polar material can be expected to have piezoelectricity if it is not forbidden by symmetry. For example, if we imagine the system where the molecules are arranged in the anti-parallel order, the ferroelectricity would be cancelled. The corollary to it is that surfaces, interfaces, and low-dimensional systems where the symmetry is broken will have the unusual form of the electromechanical coupling. So let's look at the example. So first of all, the classically surface and dimensionality effects are considered to be purely detrimental to ferro and piezoelectricity. So for tens of years, the assumption in the ferroelectric community was that the material can be ferroelectric, but the surface would be paraelectric because the surface effects will kill ferroelectricity. If we go to the small nanoparticle size, the whole particle will become paraelectric. Turns out that much more interesting phenomena exist. For example, surfaces can be piezoelectric. For example, if we have a ordered water layer on the material surface, it would be piezoelectric, whereas the bulk would be non-piezoelectric. And apparently this ordered piezoelectric water layer are really becoming more and more important in explaining a lot of unusual phenomena people see these days. Another example where the surface electrochemical phenomena become important is the electromechanics of composite and complex materials. So phenomena such as triboelectricity, cavitation, sonochemistry, sonoluminescence, they're all related to the electromechanical responses of the surface layers. Sometimes in the ferroelectric materials we can have very unusual polarization ordering. For example, the Laurent Belage group predicted that ferroelectrics will sometime develop the highly unusual toroidal state. And if you are tracing the literature now, meaning the 2019, these toroidal states are actually extremely important and as studied by the Berkeley group. Another example is the biological membranes. For example, we can hear, and hearing means that acoustic signals of the air, so the mechanical vibration of the air, can be translated in the electrical signals that our brains can analyze. So this is conversion mechanism is flex electricity in membranes, which are essentially not piezoelectric if they're flat and piezoelectric if they're bent. And it turns out that this flex electricity also exists in quantum system. For example, a graphene layer, if it is bent, it would be electromechanically active, and if it is flat, it is not. Question is, how can we probe this non-electromechanical phenomena? Well, let's first have a look how we study it in the macroscopic system. So in macroscopic system, we just take a crystal, we put 2 electrodes on it, we apply the electric field, and we start to measure strain or deformation in some form. The problem, however, that even in macroscopic system, these responses are usually very weak. For example, if we apply 1 volt to the quartz crystal, our displacement would be of the order of picometers. So this is a small fraction of the atomic radius of the hydrogen. Of course, for the quartz crystal, we can apply tens of kilovolts, and then the displacements are large enough to be measured. However, if we go on the nanoscale, for example, if we want to measure the property of the single nanoscale region, the difficulties are magnified by many orders of magnitude. If we want to measure the electromechanical coupling, we either need to measure the displacements of order of picometer, or we need to measure the currents of the order of femtoamp, depending on whether we measure the inverse or direct piezo effect, and we need to be doing it on the length scale of 1 to 10 nanometers for doing something interesting. Question is it even possible? And the answer is yes, it is. The technique called Piezoresponse force microscopy allows us to do exactly that. The main idea of the PFM is having the classical AFM setup, so you have a cantilever, you have a tip, you have a laser beam that reflects off the cantilever. We apply the electrical bias to this tip, and the application of the electrical bias creates the electric field inside the material. Here, the situation is very fortuitous from the physical viewpoint because most of the materials have higher dielectric constant than the air. In fact, virtually all materials have higher dielectric constant than the air, which means that the electric bias would be concentrated inside the material. Therefore, it will be also concentrated on the length scale of the contact radius between the tip and the surface, and that's exactly 1 to 10 nanometers. Second thing that makes us physically lucky is that AFM is very sensitive to small vertical displacements, so measuring several nanometers, several picometers, is actually pretty easy. So the combination of these two factors, the field concentration inside the material and the extreme vertical sensitivity of scanning probe microscope, actually enables the PFM. It turns out that PFM is pretty much the only way for measuring electromechanical properties on the nanoscale, so we can say that PFM is equal to nanoelectromechanics. Practically, the implementation of PFM is of course slightly more complex, so we also need to have the proper data generation, and this is how the PFM setup looked about 20 years ago. So at that time we have the AFM setup, we have the external function generator. So function generator is the device that generates the periodic wave, and this signal on the photodetector was captured and sent to the lock-in amplifier, and the lock-in amplifier is the device that actually measures the amplitude and phase of the tip-induced deflection, and this tip-induced deflection is then sent to the microscope controller and stored as the PFM signal. So this is one of the most classical implementations of PFM that is still used in multiple locations worldwide. However, now there are more complex forms of PFM that utilize either the band excitation or the DART method or the G-mode PFM. And some of these methods would be discussed throughout the following lectures. So, how does the PFM work? Imagine the single case of the barium titanate crystal, which have two ferroelectric domains, the domain with the polarization pointing up and domain with the polarization pointing down. If we apply the electric bias, the one domain will expand and another domain will contract. So for barium titanate, the typical magnitude of this expansion and contraction is about 80 picometers per volt. And if we apply 10 volts, then the displacement is a little bit less than a nanometer, very difficult to measure statically, however, very easy to measure in the periodic biasing regime. So for the positive domain, the bias and the displacement would be in phase, and in this case the phase or relative shift between the bias magnitude and the displacement magnitude would be exactly zero. The amplitude of the displacement basically tells us the strength of the piezoelectric coupling. So we can say that the amplitude of the PFM signal is the strength of the piezoelectric coupling, and phase is the domain orientation. So for domain-oriented opposite direction, the bias and displacement would be anti-phase. They would be shifted by exactly 180 degrees. Notice that for material with the polarization in plane, we also will have the shear displacement of the surface. And this is also something that can be measured in PFM. Let's look on the few examples. So this is the example of the PFM on the PZT, lead zirconite titanate. So this is the example of the topography of the ceramic sample. It was polished and then it was selectively etched. So in this case, we see the grains, for example, this one or this one. And within the grains, we see the fine features that form due to the selective etching between the positive and negative domains. Now, if we look at the PFM signal, PFM phase and PFM amplitude, you can see that, for example, this grain doesn't have any piezoelectric response. The phase here is essentially noise, and the amplitude here is almost zero. In comparison, this grain has a very nicely visible positive and negative domains corresponding to polarization pointing up and down, and beautiful picture of the amplitude. So you can see that the amplitude on the boundary between the positive and negative domain actually goes through zero, and we can clearly see a meandering domain walls going throughout the material. In this case, the domain patterns are relatively complex because this is a rhombohedral material, so we have a lot of rather beautiful domain configurations. This is another example of the PFM image of the sample which was indented by the nanoindenter. So we created a large hole inside the material. Notice that despite the fact that in this case the surface is very, very rough, so the vertical scale here is 700 nanometers, it's basically a mountain country, you can see that there is a very clear domain pattern, visible both outside of the hole and visible inside the hole as well. You can also see that the indentation actually strongly affects the domain processes. So in this particular experiment, we saw how the nanoindentation will change the domain configuration inside the material. Okay. As I said a few minutes ago, in the scanning probe experiment, we are not limited to measuring only the vertical displacement of the cantilever. In fact, we can also measure the lateral displacement of the cantilever, which is essentially a twist of the cantilever along its axis. So this is generally called the lateral PFM signal, and you can of course ask a question that displacement is the vector, what happens with the displacement component along the length of the cantilever? The answer is that this displacement will also contribute to the vertical signal, and in one of the next lectures I'm going to show you how we can quantify these dissimilar contributions to the PFM. So now if we have the PFM that measures the vertical displacement perpendicular to the surface and the in-plane displacement, we can actually combine these measurements to get a picture of the displacement vector. And this is the example of the data set when we measure the vertical PFM. So this is vertical signal. And this is the example when we measure the lateral PFM or the twisting of the cantilever. This is actually the same region of the material, and you can see that the data in the vertical and lateral PFM images is complementary. So vertical PFM, for example, shows this two black grains and all the other grains are gray. Lateral PFM image shows you that one of those grains is dark both in lateral and in vertical, and the other one is white in lateral and black in vertical. This basically means that each grain has its own vertical and lateral signal, and they in general are not correlated, so the data can be oriented in any direction. It turns out that we can actually reconstruct the full three-dimensional polarization vector. And to do that, we need to take three signals: vertical signal, lateral PFM signal, and the second lateral PFM signal when we physically rotate the sample with respect to the cantilever axis. Notice that we cannot just change the scan direction because it will not change the relative orientation of the cantilever in this. So let's look at the examples. So this is another example of the surface topography, vertical amplitude and vertical phase for the PZT ceramics. And this is the example of topography, lateral amplitude and lateral phase for the same ceramics. So if you compare these two data sets, you can see that the information in the vertical and lateral signal is complementary, as it should be. So in this case, we see bright and dark domains in the lateral signal, in the vertical signal, and we see that these domains are equally bright in the lateral signal, so we can use this data to reconstruct the domain orientations inside the material. And this is the example of the vector PFM when we have the topography, the vertical PFM signal for the ferroelectric lead titanate film deposited on platinum. We have the lateral PFM signal. We can combine these two to generate the two-dimensional Piezoresponse map, where here we map as the color the orientation of the PFM vector, and we map as the intensity of light the average magnitude. So black means that there is no PFM signal, and green means that the response signal is going in this direction, and for example purple means that it goes in this direction. And then we can separate this map further in the angular and magnetic. And this is the example of three-dimensional set. So here we work on the single crystal of the ferroelectric glass ceramics. This grain in the center is ferroelectric. The matrix around it is non-ferroelectric. If we measure the vertical PFM, you can see beautiful ferroelectric domain structure inside this grain. If we measure the lateral signal for one orientation of the cantilever and another orientation of the cantilever, you can see that we get three independent signal channels. So we map three components of the displacement vector. And of course, in this case, we have chosen this object because finding the same crystallite after physically rotating the sample is relatively straightforward. So in different samples, it would be necessary to have the fiducial marks, which allow us to find the same region and align them with each other. Now, in this case, we are able to build this full two-dimensional PFM map, and more importantly, we also can directly compare it with the EBSD. So EBSD is the electron beam technique that allows us to map the orientation of the individual domains. So we, in this case, have a map when we have the full three-dimensional map of the electromechanical response, and we have a map of the crystalline orientation. So basically, we can take these two information sources and find out what crystalline orientation gives us which value of the electromechanical response. And from that, we can, in principle, extract the values of the piezoelectric tensor for this material. So this is a very interesting study, and I will show you more examples of this type of exploration in the future. Now, how common is piezoelectricity? So far, you have seen the example of the PFM imaging of the inorganic film and the glass ceramic film. It turns out that piezoelectricity is literally everywhere. For example, if we look at the collagen film and do the PFM, we start to see the bright and dark domains corresponding to the preferential orientation of the collagen fibers. This is another example of the canine femur cartilage. So basically it's a part of the dog's bone. And you can see the polished surface, doesn't tell us really much, but then you start to see that the parts of the material develop the clearly visible domain. So interestingly enough, collagen molecules in the biological tissues tend to be organized to form bundles with the positive or with the common polarization orientation. These are more examples of this behavior. This is the antler of the deer, and in this case you can see the beautiful vector PFM map, and you can also see some details of the internal structure which are absolutely not obvious on topography. For example, here you can clearly see a region with a different polarization orientation compared to the rest of the material. So there is some internal structure of the deer bone. And this is probably one of the most beautiful examples of the wing of the butterfly, Vanessa virginiensis, where we do the PFM on it, and this is how the butterfly wing looks under the scanning probe microscope. So very characteristic structure. And in fact, the reason why the butterfly wing looks so colorful is because these nanoscale structures essentially form the photonic crystal. So the light wave diffracts of this periodic patterns and produces the bright colors. And it turns out that the butterfly wing looks equally beautiful in the PFM image. You can see that different orientations of the chitin in the wing produces different color in the PFM image, meaning that they have different orientation. So overall, nanoscale piezoelectricity is ubiquitous in biosystems, which is basically stems from the combination of polar bonding in all biomolecules and optical activity. So we know that all biopolymers are polar and all of them are optically active. This is another example of the electromechanical response, even though it's not necessarily piezoelectricity, of the red blood cells. And these are the experiments that were data was taken by our colleagues in Asylum Research. So this is the example of the red blood cells, and once we zoom in on them and take the PFM image, we start to see the additional contrast, where we see some complex internal structure, some surface features. To be honest, we don't know what these are or what these were, but it clearly shows that the PFM image always shows us additional details compared to the pure topographic image in it. There are more complex examples. So one of the objects that we have studied over 12 years ago is the tobacco mosaic virus, which is essentially the cylindrical sheath of protein which is superimposed over the internal spiral of the DNA. And this tobacco mosaic viruses are very convenient building blocks to play with for different form of nanoscale assembly and so on and so forth. So interestingly enough, these tobacco viruses also show some rather notable piezoresponse signal. And the question was, how is it possible? Because the system is clearly symmetric, and therefore the piezo effect should be cancelled. So the assumption is that in this case the electromechanical coupling is presumably flexoelectric due to the symmetry limitation, and a few years later the similar conclusions were derived by much more fundamental studies out of Berkeley group. What's interesting is that we can actually modify the viruses using the PFM. So in this case I have a virus, I have applied bias to it, and then I can just destroy this virus. So something that we will talk more in the consequent presentations. Finally, it turns out that it is possible to image the more complex objects, for example, the lung cells of the mouse. But in this case, the contrast becomes really complicated, and imaging an ambient environment is really not the right environment for the biological system. So they need to be studied in liquids, and that was one of the considerations towards extending PFM in the liquid environment, and it will also be covered in the forthcoming lectures. Now, what is the use of the normal PFM? Some of the examples that I have shown before clearly show that the PFM signal is very orientational dependent. So, in fact, PFM signal is extremely strongly depends on orientation, because the piezoelectric effect is the third rank tensor. So, for example, for tetragonal materials such as barium titanate, if the field is parallel to the c-axis of the material, the deformation is very strong. It would be about 80 volts, 80 times voltage picometers. However, if the field is perpendicular to the c-axis, then the deformation is zero. In the general case, the measured electromechanical response can be represented as the following function of the piezoelectric constant. So you can see this combination times sine square theta cosine theta plus d33 times cosine cube theta. So if we plot the dependence of the response versus angle in polar coordinates, we see this figure 8 type shape with the positive lobe being red and negative lobe being blue, which basically tells us that if we know the electromechanical response quantitatively, we can determine the crystal orientation. And what is remarkable about it is that we do it by measuring the small displacements, and we can probe this orientation in a very small region, so less than micron and more realistically less than 10 nanometers. And this is one example of the studies when we look at the protein inclusion in the tooth enamel. So this is the vertical PFM amplitude, and this is the vertical PFM phase. Notice that we start to see this beautiful shape of the protein globule inside the enamel. So this is the example when we take the vector image. So in this case, we measure both vertical and lateral component. and we see this beautiful spiral shape. Notice that this imaging also gives us extremely high spatial distribution, so in this case resolution. In this case the resolution is about less than 10 nanometers, so this is a very high veracity, very high resolution image of the protein inside the hydroxyapatite matrix. And it turns out that we can do a little bit of math to analyze what is the electromechanical response of the collagen and basically reconstruct the orientation of the collagen fibers inside the material. And we do it based solely on the electromechanical coupling measured inside the material using the PFM. Can we do it in any other way? And the answer is not that easy, because if we want to measure the orientation of the object using some measured property, we clearly cannot measure the scalar. So if we measure temperature potential, it wouldn't tell us much about the orientation, because this property doesn't depend on orientation. The second order tensors, such as dielectric constant or thermal conductivity, they tell us some information about the orientation, but typically we have to distinguish relatively small differences between one orientation and second orientation. Same as for fourth order tensor like elasticity or Kerr effect or electrostriction, they are usually weakly orientation dependent. In comparison, first order tensors or vectors like polarization, magnetization and pyroelectricity, and third order tensors such as piezoelectricity, electro-optical signal, or second harmonic generation, they contain good orientational information. However, for vectors, as you can see, we cannot tell the orientation in plane, so we can take only one selected orientation. For the third order tensor, we typically can collect enough information to reconstruct full orientation. However, there are other considerations. So we really want to measure rank 3 tensor property. We want to have the high spatial resolution, because if we don't have it, then it's really not worth doing it. And we also have to be relatively insensitive to the tip geometry, or the signal should be easy to calibrate. And then it turns out that, for example, directly measuring polarization and magnetization is actually pretty difficult, because they tend to be measured indirectly, only through the stray fields above the surface. They also tend to be fairly dependent on the probe. In comparison, as we will discuss in the forthcoming lectures, the PFM signal is actually insensitive to the tip geometry, and that's one of the extremely important factors that make PFM an incredibly useful and quantitative technique. Now, is it easy to quantify the PFM contrast? Again, this is something that we are going to discuss in the forthcoming lectures, but quantifying PFM contrast can be remarkably difficult. The reason for that, and the source of the most artifacts in the PFM imaging, is the contribution of the electrostatic forces. So imagine that our tip is in contact with the surface, so we have a surface of the material here. We will be measuring the electromechanical response of the material, but we also will be sensitive to the forces, distributed forces, acting on the cantilever. These distributed forces will result in the same type of deformation as the vertical displacement of the tip end. So the total response will contain both local and non-local contribution. So how would this look like in our measurements? So we can make a very simple analysis that in case of the positive ferroelectric domain, our measured signal would be the piezoelectric constant plus electrostatic contribution. So there is some proportionality coefficient, what we call the FNL, and this contribution would be linear in the tip surface potential difference. So this is just a capacitive force. Over the negative domain, the signal would be minus D33, so this is opposite domain, but this contribution would be the same. So it's generally sensitive only to the average surface potential. Qualitatively, it is going to look like this. So if we expect only electromechanical interaction. Then for material when we have positive, positive, and then no ferroelectric domain, the amplitude will look like this. So the amplitude is expected to be equal for positive and negative domain, and amplitude is expected to be 0 for non-ferroelectric domain. The phase is going to look like this. So the phase is positive for positive domain, the phase is negative for negative domain, and the phase would be noise for the non-ferroelectric domain. If we have the weak electrostatic contribution, it is going to shift the whole piezoelectric signal upward. As the result, the amplitudes for positive and negative domain are going to be no longer equal. So we start to see the asymmetry in the PFM amplitude. At the same time, the amplitude of a non-ferroelectric region will be no longer 0 as well. In comparison, the phase will be still positive for positive domain and negative for negative domain, but now the phase would be positive for non-ferroelectric domain as well. So there is a non-zero signal here. Now, if the electrostatic signal is very strong, so for example the surface is charged or the cantilever is strongly biased, in this case our PFM signal can look like this. So in this case our phase become uniform, so the PFM signal has positive phase everywhere, but we see strong signal difference in amplitude between the positive and negative domains. So this electrostatic contribution in the PFM signal is the most important source of the experimental artifacts, which appears over and over again. And let me show you how it looks like in the real experimental data. So this is the data on the lead zirconite titanite ceramic when we have the amplitude and phase. So this is the case where our electrochemical static signal is weak, and when it is large and negative, and when it is large and positive. Notice that for large and negative, the phase all phase become negative. For large and positive, the whole phase become positive. And notice how the relative contrast of the domains 1, 2, and 3 changes. So here, the domain has the true polarity, 1, 2, 3. Here, they have still correct polarity, but it is amplified. And here, the polarity is actually inverted, because here the electrostatic and electromechanical interactions add up, and here electrostatic and electromechanical interaction get subtracted versus each other. So this is something to pay attention, and for materials with a strong electromechanical response, such as PZT, this tends to be not such a big problem. For material with a weak electromechanical response, such as lithium niobate or thin films, this can be extremely significant problem. Question is, can we roughly estimate how strong this effect will be and what does it depend on? So it's possible to estimate this magnitude of this electrostatic force contribution as shown here. So it is dependent on the length of the cantilever, depends on the stiffness, it depends on the potential difference, it depends on the spring constant, and generally for typical material parameters, for example for 5 volts drop between tip and the surface, about 200 micron cantilever length, 30 micron width, and 15 micron tip height, for effective piezoelectric constant of material 50 picometers per volt, the critical condition is about half a Newton per meter. So everything that is stiffer than half Newton per meter will give you a pure electromechanical contrast. If your cantilever is softer than half Newton per meter, then electrostatic contribution can be important. So the ways out of the situation is to take the stiff cantilever, of course as long as material remains stable, take the cantilever which is narrow and short, try to image the nulling bias when the bias of the cantilever and the surface are maximally close. And of course, that works for many materials, for materials that can be charged, or for imaging during or after spectroscopy. This may not be possible, so there you just need to interpret the signal properly. Now, what are the applications of the PFM? So it turns out that in 25 plus years that PFM exists, it was found application in an extremely broad range of materials problems related to ferroelectric, energy materials, biosystems, and so on and so forth. So one of these applications is the imaging domains. So we can get the topography images of the material, and we can get beautiful images of the domain structures. And of course, we can also get the vector PFM images. It is domain writing. We can use the PFM in order to switch polarization and create domains. So everybody start with the drawing squares, and of course if you have a more complex setup, which now are commonplace, but 20 years ago you had to build your own, you can write the logo of the funding agencies. You can study the domain dynamics, for example the function of time or temperature, and see how the domains evolve in space. We can study quantitatively the domain evolution as a function of temperature and external parameters. We can study the spectroscopy, for example, essentially using PFM to acquire the hysteresis loops. And we can perform the switching spectroscopy mapping, where these hysteresis loops are acquired at each point on the sample surface. And then, for example, we can map the area under this hysteresis loop, and that tells us the distribution of the work of switching. We are going to discuss many of these applications in the forthcoming lectures. Now, one last point that I want to make in this lecture is the philosophy of SPM. So in other words, if you are familiar with the classical scanning probe microscopy techniques such as AFM or STM, atomic force microscopy and scanning tunneling microscopy, the question is, how is PFM related to them? And the answer is that interestingly it is complementary to these techniques in terms of mechanism. For example, the STM or conductive AFM are based on the mechanism when we apply bias and we measure current. In the AFM, we apply force and measure displacements. In techniques such as Piezoresponse microscopy or Kelvin probe microscopy, we apply bias and we measure displacement. So the signal formation mechanism, in this case, it's actually complementary to the STM and AFM. And the reason why it is important is because it affects what type of signal we measure. For example, in the current-based techniques such as STM, we measure current after we apply bias. So when current is measured by external circuit, it's actually a scalar, so current magnitude. Bias is a scalar, so the measured signal is scalar in nature. And this signal scales with the contact radius. So if in the classical regime, it scales like a size of the contact area. In the tunneling regime, well, we talk about the tunneling, so it's point contact. And in the intermediate Charvin regime, it scales at the square of the contact radius. In the classical force techniques, when we apply force and measure displacement, well, force is a vector, displacement is a vector. So basically, the measured signal is the second-rank tensor. The only problem is that due to the specificity of the AFM cantilever, we cannot really measure the contributions of the signal that fall along the cantilever axis. So as a result, we practically can measure only the lateral and vertical AFM signals. So we measure only specific elements of this matrix. Secondly, we know that our contact stiffness scales as the first power of the contact radius. And this is extremely important because the contact radius is affected both by the tip shape and by the surface topography, which basically means that AFM as a technique can be quantitative only if the surface is absolutely flat or we somehow know the contact radius. If we don't know it, then AFM is actually not quantitative, and this is something that is very well recognized in the nanoannotation community. And for example, all of our FAR method for nanoannotation testing is explicitly designed to stabilize the contact radius. In AFM, this is generally impossible, and therefore the universal perception is that AFM is not quantitative technique, and generally it is correct. So it becomes quantitative, however, once we go to the single atom or molecule level. So once we do something like molecular unfolding spectroscopy, when the cross-section is one molecule, then our signal does not depend on the contact radius, and it is quantitative. In comparison, the electromechanical techniques such as PFM, here we apply bias and we measure displacement. So our measured signal is a tensor, so that's what we measure in the vector PFM. And what is extremely interesting is that in the classical regime, the measured electromechanical response does not depend on the contact radius. This is a fundamental fact, so this can be obtained from both the order of both dimensionality theory and from more complex theory. But this is extremely important because that means that the PFM signal is quantitative. And many of the developments in the field of PFM, including quantitative spectroscopies, imaging, even the fact that we can get high contrast, very high fidelity images, utilizes the fact that the signal is independent of the contact area and the PFM signal is quantitative. And I will talk about it more in the future lecture. So, just to wrap this introductory lecture, let me speculate a little bit about the future. So where would the PFM be in 5 to 10 years from now? And the answer is that one of the opportunities going forward is to go beyond the purely electronic properties in nano devices. So we all know that semiconductor electronics now is approaching below 10 nanometer level, and with the quantum materials and devices it goes on the single atom level. However, if we talk about the nano machines or nano robots that perform all kind of useful functions, they actually need to actually to not only think but also move on the nanoscale. In other words, we need to efficiently transduct electricity and the mechanical motion. So for that, we need materials that can efficiently transform electrical energy to mechanical and vice versa. And this can be molecular machines, that can be biological systems, and so on and so forth. But we also need the experimental techniques that are capable of addressing electromechanical energy transformations on the submicron, nanometer, and molecular scale. And PFM is such technique, and I hope that you are going to enjoy the content of the forthcoming lectures that talk about its mechanism, dynamic, and application. So let me also show you several references. So this is a set of papers from predominantly work done in Oak Ridge, but also from other groups that talks about the applications of PFM. So these are the examples of the work for combined the BSD and PFM imaging, the introduction of the vector piezoresponse microscopy, applications of the PFM for biological systems, and several general references which summarize the overviews of the PFM imaging for biosystem, for liquid imaging, and cellular materials. Thank you.